Thank you so much for joining. David Guedalia. At VATbox, a quick introduction to what we do here. We recover VAT. VAT is MAM, value-added tax. And recovering VAT sounds like a very simple thing. You know, you come into the airport, you hand in your receipts, and you say, here's my receipt. I want my VAT back because I spent money in a foreign country. Try doing that for 100 million receipts in one day. It's a little bit harder. That's why we have computers, and we're very thankful. So we use AI to analyze receipts at a large scale, and then ensure compliance, and then go through the regulatory authorities. We've been doing this for a bit. So we got IP, we got lots of clients, and there's lots of money going back and forth. It's a big world of money. I wanted to spend 1 or 2 minutes just talking about how we look at an invoice and data science at VATbox, because you're all welcome to apply for the jobs we have open here, and you'd want to know what you do if you come here. So here's 5 minutes on what we do at VATbox, just a little bit lower level. And then it's going to leverage that into the next conversation about how I view categorical clustering. So I don't know how many of you are familiar with that problem, but I want to dive into that problem in a minute. So first, what's a receipt? You go to Starbucks, you buy a cup of coffee, they give you a receipt. Very nice. What does it say on the receipt? So the first thing we do is we look at the pixels. We get an idea of the structure of the document. We analyze the structure of the document. Here we did some clustering, and we colored each part of the document differently. Then we can dive down, and we can start to extract information from the document. Things we need to do. The next level up. So we have the pixels. We have the structure of the pixels. Now we can talk about the words. So there's a hierarchy of information being constructed. You look at the words, you can look at the relationship between words. What words appear often next to other words? It's kind of standard today. You look in the word2vec world. Here I put them on a graph, and you get to see certain words are relatively close to other words. I'm going to come back to this tool in a minute. So we're using a graph to try and analyze word relationships. Then you go up a level to semantics. What country was the receipt in? So now it's not about the pixels, it's not about the structure or where they are, it's not about the words, it's about where, which is a word, which is a concept already. And then you have things like the date and the currency and the information that the traveler used and all sorts of external information we need to do currency conversions, the amount of the expense, what type of an expense was it, were you at a restaurant, were you in a hotel, were you eating in a hotel? And one of the harder problems we have is, where did you do this? So there are 3 Hiltons in Berlin. Which Hilton were you at? Things like that. Once we've gathered all that data, and we enriched the data, and we need to make a decision. Now the kind of decisions we first need to make are going to sound a little funny. But the kind of questions we ask are, is $10 a lot for a cup of coffee? Right? That's almost a sensible question, but it depends on the policy of the company. It depends on what country you are. Okay? Is Sunday very far away from a Saturday? So in English, it sounds a little funny. I tried it with my father, and he was saying, what do you mean is Sunday farther than away? No, it's a real question, right? I want to know, you had an expense. You paid $10 for a cup of coffee on Sunday, paid $10 for a cup of coffee on a Tuesday. Does it make sense? So if Sunday and Tuesday, if I can measure the distance between Sunday and Tuesday, I can start to measure the distance between a cup of coffee on a Sunday and a cup of coffee on a Tuesday. To do that, I need to be able to talk in categories. So I'm not talking about numbers anymore. I'm talking about Sunday and Tuesday. These are 2 different categories. They're symbols. So how do you do metrics in categorical space? Famous problem. But that's the problem we're working in. And it's going to come up again. And when we talk about NLP, talk about words, what's the difference between different words? So that's the core problem. Before I dive into that problem, I want to show you that it's actually a very fundamental problem that even exists in things that you wouldn't think. So here's some data I took. So I pinched some data from Kaggle, nutritional data. What you see here is different types of food. There's a nutritional database with about 1,000 types of food. So here you have beef shoulder, young leaves, cheese, cheddar cheese, fruit cocktail. So there are different items of food, about 1,000 of them. For each item, there's a nutritional spec. How many calories, how much protein, how much fat. You can break it down. There are about 50 qualities of nutrients for every single one of the foods. Okay, you close your eyes. I've given you a data frame. The data frame has numbers in it, and I say, cluster the data. Right? Show me which types of food are close to which types of food. It's an easy question. It's not so hard to do. Take a data frame, download sklearn, run some sort of clustering. Voila, it should work. So I did that. So here I'm using UMAP to display it. Then I did a DB scan on that too. And what we're doing here is basically doing an embedding. And I put the picture here to kind of give some context. In the NLP world, you talk about embeddings all the time. You take words, you embed them into a numeric space. Word to vec, Bert, whatever it could be. Why do you do that? So that you have numbers. Now we can work in the number space, the numeric space. I can say, look, this is on a scale of minus 15 to 10, and at a scale to 10, I have 2 dots. I can measure the Euclidean distance between those dots, and then I know how similar things are. Okay, who believes this is going to work? Right? Why won't it work? Well, what does it do? So here's an example. I put some labels on it. Now, one of the problems at this point, I don't know if you've experienced this, but I suffer this, is I'm not like super really good at PyPlot. But when you try and PyPlot this is what it looks like. Like you start to annotate it, and you have to, it's not the best tool. I don't know how many of you suffered through this tool. Maybe you have a much better way of doing it. But the first 3 steps are really easy. Boom, pandas, read CSV, get the nutritional data, get a data frame, run UMAP, HTTP scan it, boom, you can color it now. I don't know if you can see the colors back there. Annotate it in PyPlot. What do you see? Oil is in the middle of nowhere. Then you have a bunch of stuff here. Among the things you have here, so here I have salmon, pork, beef, elk. That kind of makes sense. Beef and elk should be kind of close to each other. Cereals, pork again, cereals. So somehow the 2 cereals got separated by pork. Bagels, it's kind of hard to read it. This is my favorite one though. I don't know if you can see it. I don't know how to pronounce it. Agutuk, meat caribou, in parentheses, Alaskan ice cream. So I had to look it up. I don't know if you know what agutuk is. Anybody here know what agutuk is?
Caribou, it's like a kind of reindeer.
Yeah. So what is agutuk? And why is it called Alaskan ice cream? It's a ground meat. In Alaska, they take caribou meat, they grind it up, and it's like potluck. It's just like a poke. You know, you just kind of take whatever food you have, chop it into little bits, and you create agutuk, and it's what you eat when you're cold, I guess, all the time. Okay, but where is it sitting? So it's sitting right next to ice creams, Breyer's ice cream. Now, the funny thing is, when I first saw it, I thought, oh, Alaskan ice cream, Breyer's ice cream. That worked out well. But then you look up agutuk, no, it's meat. So what it means is that when you take the nutritional information as it is, as numeric data, and you map it down, and you try and see what foods are close to each other, you're going to have meat is close to ice cream, which is treif. That's not good. You're going to have pork, which is treif, next to elk and beef. That kind of worked, but you're going to have beef down here and pork over here. It's a mess. I mean, maybe you think this is good. I had a very hard time making pretend it was good. Okay, so why doesn't this work? That's the question. I mean, what did we do wrong? We used all the right tools. Yeah.
What did you expect from the clustering? Because you clustered according to their nutritional value, right?
Right.
So what did you expect the clustering would give you?
So I would expect foods that are similar should have the same nutritional values. So a beef and lamb and meat from other animals should all more or less have the same thing, as opposed to, let's say, milk and cheese, which has some fat, as opposed to cereal, which should be. But I'd expect each type of food to be different.
But if you have something like a meat pie will be somewhere between
right.
bread and meat.
I agree, but agutuk, which is more like a meat pie, is between macaroni and cheese and hydrolyzed vegetable something. It's not in any world that it should be.
And when you looked at the nutritional values themselves, did you see that it's really different? Because, I mean, it's really strange that they cluster this way if they aren't.
Okay, so let's take that as a question. Let's assume that this is real, this is what happened. Why would it cluster this way? So I want to give my explanation first, and then you're welcome to shoot it down.
Some of the items, this is not listed. The ingredient is not listed.
So it's not by ingredients, it's by micro and macronutrients. It's protein, carbs, fat. It's not the ingredients of that. I don't know.
What they say, if you have extra ingredients, you change the composition of the milk.
Right, so you're going to say something like...
if you had sugar, you had a lot of...
Right, so all the cereals I'd expect to see together because they all have a lot of sugar in them, for example.
You have healthy cereals with no sugar. And
yeah, but honey clusters, but you're right. But that's what I would expect to see, and I'll go forward, you'll see that that's what happens when you do it the right way.
There's only types of nutrients, right?
No, it's been mapped down. There are 52 nutrients, and I used UMAP to map it to 2 dimensions. What UMAP does, it's a painful description, but it creates a graph, and then it maps the graph down to 2 dimensions. It's a way of dimensionality reduction. You could do it with like a PCA as well. You could do it in different ways. UMAP is the fancy way of doing it. But let me try and convince you why I think this is broken and will never work. Like, there's a fundamental flaw here in the logic. And it's not that hard to see it. So the first flaw is, and this, I failed miserably in high school, physics, but notice your metrics. They're milligrams and they're grams. And you're just taking the data and saying, oh, it's all the same, grams and milligrams. It's not going to work, right? So you have to normalize your data. You have to make everything the same metric. Everything should be grams, everything should be milligrams. Step number one. Okay, but it's worse. Because even if they're all milligrams, the numbers in calciums are in the hundreds. In iron is in the low single digits. Again, you got to normalize it, maybe between 0 and 1. Okay, so I normalized all my data. Is that going to work? No. Now I want to tell you why that's not going to work either. But that's the easy reasons why this didn't work. Right? The easy reason is because I didn't normalize the data and I just assumed, oh, I can just measure distances on numbers. No. But even if you normalize data, there's a fundamental flaw. That is, and a lot of words here, but things aren't linear. What does that mean? Nutrients have a typical S-curve, which means that at a certain point they do very little. Then they start to function. The more you have, the better. And then at some point they become toxic. So a good example is like selenium. Selenium is found in Brazil nuts at a high value, high levels. There are all these rules of thumb. If you have more than 4 Brazil nuts a day, you can cause great neurological damage. You should be very careful, etc. Right? So different people have different levels of what the body can handle. But it's not linear. So if you do a little bit more, at some point it becomes toxic. What does that mean? It means that if I have 2 foods, and one has, and I normalize them, and I'm fine, right? All my numbers are from 0 to 1, but one has a little bit more than the other, it's not a metric distance. Because of the behavior of the nutrient, it became a nonlinear function. So if you look at, for example, how foods have selenium, most foods have very little selenium, and it's kind of all a bunch of foods in this neighborhood. There are a couple out here in Never Never Land. Kidneys, Brazil nuts, whatever it could be, they're over here. What does that mean? It means that most humans don't eat this food because it would kill them. So they eat this food, right? So the numeric mistake that we're all making, I'm assuming, I made, and I assume we all make, is we assume that there's a linear function in the way the numbers work, and that our distance metrics work. And then after I normalize the data, I'm happy. And then if I embed my data, that's it, I'm okay, right? That's false. I hope I convinced you. If I didn't convince you, make pretend. Okay, make pretend is false. But it is false. So step number 1 is to remember numeric data is not going to work either. So what works is to bring it back to categories. So I want to treat everything as non-continuous. Everything is a category. Now that's going to cause new problems because dealing with categories is a much harder problem. Life was so easy when I had numbers. I could do things like gradient descent. I could do things like Euclidean distance. Life is easy. No, we're going to go into the world of categories and symbols. And now you're going to say, well, how do I learn anything? What's the difference between a red-orange and a blue-orange? Okay, one's red, one's blue. What's the difference between red and blue? They're colors, hard to know. What's the difference between Sunday and Tuesday? But you can measure that. So how do you measure the different distance between categories? You look at the context where those categories are used. So I have a data distribution. And then I say, okay, given this data distribution, now how do I relate to certain days? So in Israel, we relate to Sunday very differently than people in America relate to Sunday. Right? Saturday, Sunday, it's a very different experience. So our semantics have developed a way that relates to our behaviors, which relates to the way the data actually distributes. So we want to do categories, and then we want to look at the relationship between the categories over many observations. How do we do that? Use a graph. So the first thing I'm going to do is I'm going to take my numbers. I'm back in the numbers. And I quantize my numbers. So I took my nutritional data. Here's a little bit of code. I use k-means. Really, it's done in 2 lines, but then I went ahead and I wanted to relabel everything to be pretty. So I have column names, and my column names are things like cholesterol value. And what I did was I got buckets. Think of it like a histogram. I just took the data, divided it up using k-means, and now I have buckets of all the food types that are in the neighborhood of 62 milligrams of cholesterol. 3, etc. So here's selenium again. And you see there are a couple of different buckets, 39, 58, 96, 176. And you see these are foods that are in each type of bucket. So I quantized it. So now when I say selenium 39, I don't mean the number 39. I mean the category. The category 39 means all these types of food. Right? So what's the distance between 39 and 58? I don't know yet. It's not whatever the number would be. 17, 18, 19? Not 19. It's not 19. 39 to 58 is two different categories. It could be 58's toxic, right? Between 96 and 176, it could be it's toxic at that point. All I know is I have categories. So step one is take your numerical data, quantize it into categories. So far, so good? That was the easy part.
But we're ordering the categories.
Maybe yes, maybe no. You never know. Like for all you know, it could be that humans love a ton of selenium, they hate a little bit, and they love a little bit. Like it's not clear. We have to assume that there's no immediate metric between the categories. That's my assumption. They're kind of randomly labeled, but I know they're distinct. Step one.
Decide on the bidding.
I used k-means and I just threw a number in. It was bad. It's not good, but I'm going to argue that it doesn't matter that much because as long as you're somewhere in the neighborhood, it's fine. Okay, so now here's the category that got for selenium, and you kind of get an idea of how it's distributed. And now we're going to do the next piece of magic. Another piece of code. What we're going to do is very simply, and again, it's like 3 lines that I could have done in an apply statement maybe or a pivot, but you want to rename things so it comes out okay. And here's the trick. The trick is, it's a big trick. For every food type, which is an observation, I had a category, remember, not a numeric value, a category that was associated with that food type. So black beans have 14 calcium milligrams. Boom, I'm going to create a graph with an edge with a weight of 1 between black beans and the category calcium 14. So now these are all categories, they all become nodes in my graph. Right? I don't know anything about them. I don't know the relationship between them, but I know I have a lot of food that relates to each one of these categories. So now if I have a lot of beef that all goes to the same category, I'm going to get a cluster of nodes around that. But wait, if the beef also relates to leucine, then I'll know that leucine and cholesterol, let's say, are related to each other through beef. Okay, so that's the whole trick. The whole trick is going to be now, categorize your data, if it's numeric or not, and then using multiple observations, create a graph that gives you the relationships between the data. So this is what the graph's going to look like. So this is using Gephi. Gephi is this great little program that you can load up a graph. So I don't think I had all the code there, but it's like 5 lines of code. You know, it's create your edges, right? I had a data frame. I mapped out my categories, quantized them. Then I created from to to graph, an edge list. Then I took that, I loaded it into network X, 1 line there. Then I saved that. And I loaded in Gephi. Gephi is a great tool. So in Gephi, each color here, now what I did was I first created the graph. Their nodes, the center nodes are going to be the categories we'll see in a minute. The edges are going to be, all the other little nodes are going to be the different food types. I then, in network X, partitioned the graph. So I created communities, groups, clustering. I then color them, and boom, now you have colors. So each color represents a different cluster of food types that are associated with a category. So if I zoom in, what you see is, let's say first the categories. Sugar, magnesium, potassium, choline, zinc. And I can tell you, because I'm cheating, things with high zinc and high choline end up being beef. And so if we zoom in again, let's see if it worked, we can start to see things. So in this world, I have beef, beef, beef. Alaskan ice cream, agutak. Beef, beef, beef. I didn't do it, really, that's what happened. I did nothing. It was a good shankboat, right? It's a good demo because it worked. The miracle agutak meat ended up in the middle of a world of meat and beef. Why? Because I'm not doing the ugly thing of non-normalizing my data, normalizing my data, and then treating everything. No, it's all categories. It's all a function of how it relates to all the other data. Okay, so that was fun and exciting, and it worked. And I can show you another example of where it's so exciting. But now I want to take you to the next level. Okay, so this was all the introduction. So the introduction was categorical learning works. Not only does it works much better than numerical learning. Why? Because most times it's really hard to normalize your data when it's numeric. And you always assume that it's well and normalized, and it's not. So don't even try. Okay, step 1. Convert everything to the categorical. But wait, how do you do categorical learning? So I gave you a technique. My favorite technique, use a graph, use partitioning. Partitioning is amazing because it automatically finds that magic K. You don't have to worry about K-means what the K is. Partitioning works. And you have tools like Gephi, which are great, and I'll show them to you maybe in more detail. So that's all magical. Now what do you do with that to make it pretty? Because magic is good, but pretty is even better. So Imagenet. So we all know Imagenet, I assume. A lot of us know Imagenet. Imagenet is a bunch of images, and the goal of the task is to find the class of each image. Okay, all these images are frogs. They all have the same class frog. And you look at the images, and you're supposed to say they're a frog. And you can see that some of them are harder than others. Well, harder in the sense it's very different. It's a very broad distribution of images. These are all the same class lizard. This is my favorite one. The hot dog is a dog. So all these images are dog, and you're supposed to build a network that does a dog. So now when you look at Imagenet, what happens today is it's the world of deep learning. It was propelled by Imagenet. I mean, this was the thing that made deep learning famous. So Imagenet today is a database of over 1 million images with 1,000 categories. It's about 1,000 to 1 ratio. And then you train your deep learning network on this, and Google's very happy, and NVIDIA is even happier because you're using a huge amount of processing power, and then you get wonderful, exciting results. Then they took Imagenet. I'm going to sell something which maybe I shouldn't sell here or not. And then they took Imagenet, and they said, well, it works so well, why don't we use the same idea for autonomous vehicles? So I was working at Mobileye, and every autonomous vehicle company is going to tell you, what do? Oh, yeah, we take images, we train them, deep learning, boom, it works, great. Until you have people that come along and put little stickers on signs, and then it fails. So there's a whole world of work being done now in how to undermine the deep learning in these image learning networks, right? And I'm sure most of you are familiar with this, so that's not a surprise. So then the next step is to say, well, why is the learning failing? And the answer is because you're overfitting. Well, why are you overfitting? You have all these images. Well, I'm overfitting because I'm doing an embedding, a bad embedding, my answer. And the bad embedding is being leveraged to create a bad classification. So I want to try and convince you that the right way to do an ImageNet solution is, yes, to do some sort of deep learning, but to do it in a categorical space, not a numeric space. Avoid numbers when you can. So I took ImageNet. So here's a soccer ball example. Again, look at the diversity because it's important to get the feel for it. And you take an image from ImageNet. I quantize it here. Exact same thing I did last time around. K-means. It's just take a band of the image. Here it took U, I think. And then quantize it down to some number. I don't know, 10, 32, something. Okay, so these are pixels, 180 by 189 pixels. Now I'm going to take 3 by 3. When I look here at this, I can take a 3 by 3 window. I can define characteristics of a 3 by 3 window in categorical space. So again, each one of these pixels, it's like you said, it's not that they have relative values anymore. I don't know if number 1 or number 2 are close to each other or not. They're just categories because it's random. K-means went ahead and gave different centroid numbers to each pixel. When I quantize, I just put in the centroid numbers. Okay? Now I say I have a 3 by 3 block. It has these numbers in it. 1, 1, 1, 1, 1. Well, that's easy. They're all the same. Okay, so I have a measure of entropy. What's the entropy in the 3 by 3 block? I can do that with my categories. I can also measure how much of the horizontal is similar to the vertical. Again, all I'm saying is identical categories in the window, non-numeric functions. Okay, I do that, and I get my graphs. Same thing I did last time. I create a graph. I have nodes, center nodes, which are the feature space, so to speak, the entropy, the different types of entropies. My little dots, the external nodes, are the 3 by 3 blocks. Boom, you get this pretty graph in Gephi. Now I can go back, I can recolor my image, and I can do it hierarchically. So I take my original image, I break it down, I break it down, I break it down, I break it down. At each step, I did exactly the same thing. I'll show you the code. It's like a little loop. You just do the same thing again and again. You take 3 by 3 blocks, you quantize, you graph, you cluster, you label, you do it again, 3 by 3 blocks, and again. So I can create a hierarchy, and I can create a deep learning, so to speak, and I've done 0 gradient descent, 0 numbers. It's all categorical.
How much time each loop takes?
It depends on my laptop, on 1 core, a couple of seconds per image. Like this entire image I can do in about a second or 2. I mean, you could do it faster if I tried, but I didn't try. It's written in Python and has loops.
Relative to our first ImageNet is. It's faster, it's equal.
I assume it's a lot faster because I didn't do the math. Because an Imagenet originally used to take a couple of weeks to train off an Imagenet. Now I don't know. Now they use a farm of.
The influence of what you are doing.
Yeah, I think this should be a lot faster. But to know that it is, I can't tell you because I didn't do the math. Okay, so then again, I'm just showing there the graph with some labels on it. Right, I mentioned that I think like entropy. Entropy 0 means everything the same color. So all these pixels had basically the same color. They all were quantized into the same color. All these blocks of 3 by 3. Now if you look at this picture, it says something about the image. It says, oh, how did the blocks distribute? Well, a whole bunch of them distributed here. Now if I put up a different image that doesn't have uniform sections, you're not going to get this big blob here around entropy 0. So I can now create signals based on that. So I create signals, and now I can go back to my entire data set. So now I went back to my data set that had all those cats and dogs and soccer balls and lizards. I took all my images. I went through that little process, and now I can graph that. So what I did here was I first graphed pixels. Then I graphed 3 by 3 blocks of pixels. Then I graphed 3 by 3 of those 3 by 3, all of a single image. Then I took all my images and I graphed all my images, and here's a graph of all my images based on those 3 hierarchies of those 3 other graphs. I don't know if that makes sense. Okay, so I have three time hierarchy of graph, take something from that, and then graph an entire image. Now I take all your images and graph those, and this is what you get. Well, so to be fair, if you only looked at the lower level, this is what you would get. And I have the different names of the scene sets, the different titles of each type of class. You see things like soccer ball, payphone, taouf, payphone, rapesy. So what it says to me at this point is, at the lowest level, most of the classes are randomly distributed. If I look at a 3 by 3 block of pixels, they're all over the place. But then when I go up a level, I can start to see organization. Pizza, American chameleon, bullfrog, right? Again, this is entirely unsupervised. Nothing happened. I mean, I may say weak supervision. The supervision that occurred here is that to create this, I chose a data set. But until I chose that data set, there was 0 supervision. When I chose the data set, it's a weak form of supervision, and now I'm graphing it. And so what you see as you go in, I don't know if you can see from so far away, is at the lowest level, say soccer ball is all over the place. It distributes along all the images. When you go up a level, it gets more centralized. And when you get to the highest level, it kind of divides into 3 types of soccer ball images. So you saw the image of the soccer ball. It makes sense. If you're sitting and you're looking only at the ball part, they all look alike. When you step back, there are all these other things in the image. So it kind of breaks up. There's different types of soccer balls. Okay, so that was a game I played, and it was a lot of fun. And here are my take-home messages. It's possible to do deep learning, I'm calling this deep learning because it's a hierarchy, in symbolic networks. No gradient descent, fully symbolic learning. This is really important to me because I was listening to the AI debate between Bengio and Marcus. I don't know how many heard it. And this was a conversation. Neat. This is the process I went through. Create 3 blocks, signatures, graph. Okay. If nothing else, I'd like you to take home that there's numeric analysis, categorical analysis, different tools for each one. And I'm a big fan of the categorical analysis with graphs and Gephi, and colors work. And then I just put a little graph up to show you that in the Imagenet world, it actually does seem to work. As you add data, you get better numbers. So I have relatively very small data set. I have 20 different categories and only 35 images per category, and that's considered a small number as opposed to 1,000 to 1. It's 30 to 1, and I'm getting reasonable numbers. I ran this by somebody. It sounds like reasonable numbers.
Did you process all the Imagenet data?
No, I did not. No, I should one day. But actually, that would be a. I think
the same amount of data.
Right, so I need to compare other people, but other people don't do Imagenet, which is small amounts of data. There's another data set I found people use, I just found this out yesterday, called Cubes, C-U-B, Cubs, anyway, which is a smaller data set. There's also tiny Imagenet, which they use to do few-shot learning and one-shot learning. That's this field. So this is now in the world of few-shot learning, where you have very few samples and you want to use them. Okay, thank you. Any other questions? Any other thoughts? Anybody want beer? Yeah.
Classification of food.
Food, yes.
Why do you not using knowledge bases, for instance, word network, you have a category immediately.
Right.
You don't need a trick.
Right. So primarily I was trying to find a database that had numbers in it. So when I wanted to classify the food, I wanted to use the numbers to show you that that was a bad way of doing it. You're right. Maybe a much better way to do food would be, say, I have a document and see how people eat food. And then you could analyze behavior analysis on the food, and that would be much more informative. Yes. But this was my attempt to show you that the RDA is wrong. When you just look at numbers, you get nothing, and you have to actually see how food functions as a behavioral substance. Yeah. Okay, fair enough. Yeah, you had a question?
Did you ever consider like trees in that discussion? Because that would seem like the halfway between categorical.
Yeah. So in the Imagenet example, I use random forest then to do some classification. So I do use trees. But when you say to use trees in a supervised way and unsupervised way? In supervised way. So I think that's fair enough that would be, yes, the right solution, is that you use unsupervised to get you to a certain point, and then when you need a supervised classification or labeling, you can use a tree, which is also kind of symbolic, yeah. Yeah.
Have you tried log transforming your data? Compress the dynamic range?
Right, so focus on the image examples. So basically what I'm doing is some type of compression, right? I'm taking the image.
The food.
Well, I did the UMAP. The UMAP is a compression type, if you think about it, because it takes the 52 dimensions and it projects it down to 2.
I mean, for the numerical data, you have some which have like milligrams and some which have grams. And this creates some problem even after you normalize it. So if you log transform for normalization, you may circumvent this issue.
I agree. To a degree, I was hoping that that's what the UMAP was going to do. Right, I took the data here and here.
Well, you don't know what actually it's doing.
Well, what it's doing is, theoretically, it's taking all the data, and then it's taking the multi-dimensions, and then it's seeing the relationships, creating a graph, and it's trying to project it out the dimensions. So it's trying to do that.
If one of your dimensions is very high dynamic range,
I agree.
And you get a problem in this kind of...
I agree. I cheated here because I gave a really simple example where the data had multiple things that need to be normalized. Also, the scales were wrong, and also the data wasn't normalized that way. But in addition, I'm arguing that all numeric data needs to be normalized beyond what it can be. Normalization is very hard to do properly. So that's why I'm arguing to avoid it, use quantization. But you're right, I could have done better on the nutritional data if I tried. But then I wouldn't have learned about agatak. Like, who would have thought? Okay, thank you.